Continuing with the section 3.2 notes, let's look at example 1. Describe the end behavior of the graph of the polynomial function by applying the leading term test. First example is f of x equals minus 3x to the fourth plus 4x cubed minus 2. Our focus needs to be just on the leading term, minus 3x to the fourth. And looking at that term, we see that the degree of the polynomial is even and the leading coefficient is negative. Okay, now looking at our three cases above, if we have even degree and a negative leading coefficient, that's case 2. And the behavior of the graph of this function to the left and to the right should be the same as that of an inverted parabola, minus 1x squared. So we can say that the graph will eventually fall to the left and fall to the right. Now, it would be sufficient just to say falls to the left and falls to the right. I'm stating it in a little bit more detail since the in-between behavior of the function is not clear to us without looking into things more closely. But we do know the eventual behavior will be like what we see with the inverted parabola. So with example 1a, what we might actually see with the graph is, perhaps something like that. But to the left and to the right, eventually it's going to fall in both directions. Example 1b, g of x equals 1 plus x to the fifth. Here actually the leading term is not the first term, but we just look for the highest power of x in determining the leading term. What we see is the degree is 5, it's odd degree with a positive leading coefficient, positive 1. So the behavior here should be what we see in case 3. Just like the graph of f of x equals 1x cubed, the graph will eventually fall to the left and rise to the right. It may look a little bit different in between, but to the left and to the right, the behavior will be the same. So the graph falls to the left and rises to the right. In fact, it turns out that the graph of this function g of x would look rather similar to the graph of f of x equals x cubed. Just a couple of modifications, but it would look quite similar actually to the graph that's shown above under case 3. We now turn to a topic that's very important for the understanding of polynomial functions, and that is their zeros. So we'll spend quite a bit of time on this topic. Basically, a number c is a zero of a function f if f of c equals 0. So a zero of a function is a number when substituted into the function causes it to equal 0. Another way we can say it is that x equals c is a solution or root of the equation f of x equals 0. And why is that? Because if c is substituted for x, the equation is satisfied. F of c equals 0. So c is a solution or root of the equation. If c is a real number, then the point c0 is an x-intercept of the graph of the function y equals f of x. So another interpretation, assuming we're dealing with a real number 0, is that we're looking for x-intercepts. That's because when we substitute x equals c into the function, the function value is 0, which means the y value is 0. And that means we have found an x-intercept. So to say we have a 0 is also to say we have a solution of an equation. And in the case of real zeros is also to say that we have an x-intercept of the graph. So these three ideas are very, very closely connected to each other. If f is a polynomial function of degree n, then f has at most n distinct zeros, and the graph of f has at most n minus 1 turning points. We'll look at this in more detail as we look at some other examples, but one of the important things we note about polynomial functions is that their degree will determine how many zeros they can possibly have. Let's say we have a fourth degree polynomial function. A fourth degree polynomial function can have a maximum of 4 distinct zeros. It may have fewer zeros than 4 if we're counting distinct zeros, but it can have no more than 4 distinct zeros. Also, its graph, the number of turning points on the graph is limited by the degree as well. To 1, the number of turning points is 1 less than the degree. So if we have a fourth degree polynomial, its graph can have at most 3 turning points. It may have fewer than 3 turning points, but it can have no more than 3 turning points. Zeros of polynomial functions can also be identified with factors. So we mentioned zeros, solutions of equations, x-intercepts. Here's a fourth thing that's connected with those other 3, and that's with factors. For example, the function f of x equals x cubed minus 6x squared plus 9x can be written in factored form as f of x equals x times x minus 3 squared. It's not difficult to factor that particular polynomial. The factor x is associated with the 0, 0. That is, 0 is a 0 of the polynomial because f of 0 equals 0. And the factor x minus 3 is associated with the 0, 3. That is, f of 3 is equal to 0. So x minus 3 is a factor. The 0, 3 is referred to as a repeated 0 since it's associated with a factor of f that occurs multiple times. There are actually 2 factors of f associated with the 0 of 3. The x minus 3 squared is really like having 2 factors of x minus 3 times x minus 3. We say 0 is a 0 of multiplicity 1 because it's associated with a factor that occurs only once, and that factor is x. And in our factored form here, we could write that as x to the first power. So the multiplicity would be associated with that exponent. And we say 3 is a 0 of multiplicity 2 because when we write its factors with its repeated factor with an exponent, that exponent is a 2. Now, in describing these repeated factors, these repeated zeros, the technical term for this is multiplicity. Given a polynomial function f, a number c is called a 0 of multiplicity m of f if c is associated with a factor that occurs m times when f is factored completely. So if we see that a particular 0 is associated with a factor that is repeated a certain number of times, let's say 3 times, then we say that that 0 has a multiplicity of 3. If we have the complete factored form of a polynomial, it's easy to identify the zeros and their multiplicities by looking at the factors. And we can determine the zeros of a polynomial in the same fashion we would have when we solved equations in algebra. Example 2 says, identify the zeros of the function and state their multiplicities. If I set the function equal to 0 and solve the resulting equation, we know from algebra that if we have the product of factors equal to 0, it means that we could set each factor individually to 0, x squared x minus 2 or x plus 5 in this case, and by solving the equation, come up with a solution of the equation f of x equals 0. For x squared equals 0, that's just x equals 0. For x minus 2 equals 0, that's x equals 2. And for x plus 5 equals 0, that's x equals negative 5. So the zeros of the polynomial are 0, 2, and negative 5. Now, if we look at the factors associated with those zeros, notice that the factor x associated with x equals 0 occurs twice. The factor x minus 2 associated with x equals 2 occurs once. And the factor x plus 5 associated with the 0, negative 5 occurs 3 times. Well, the number of times the factor occurs corresponds to the multiplicity of the 0. So we would say that x equals 0 has multiplicity 2, x equals 2 has multiplicity 1, and x equals negative 5 has multiplicity 3. For the second example, the difference here is that the polynomial is not written in a factored form, so we have to factor it ourselves. In this case, we notice that each term has a factor of x. So let me factor that out of each term. If I factor an x out, I'm left with 4x squared plus 4x plus 1. And then if I factor 4x squared plus 4x plus 1, we can try 2x and 2x perhaps, and 1 and 1. And if we check by FOIL, the inner and outer products, we get 2x plus 2x, that gives us 4x. So all of the terms are accounted for, and we have the factored form of the polynomial. Now, since 2x plus 1 is a repeated factor, we can write it as x times 2x plus 1 squared. So we have x to the first, just for emphasis I'll put a 1 there, and 2x plus 1 squared. Now for x to the first, we have x equal to 0 as a solution of the equation g of x equals 0. And for 2x plus 1, if we set that to 0, subtract 1 from both sides, and divide both sides by 2, we get x equals negative 1/2. So the zeros are x equals 0 and x equals negative 1/2. What about the multiplicities? Well, the factor that gave us x equals 0 occurred only once, x to the first. So the multiplicity of 0 is 1. The factor that gave us x equals negative 1/2, 2x plus 1, occurred twice, 2x plus 1 squared. So the multiplicity of negative 1/2 is 2. There's an important connection between the multiplicity of a 0 and the behavior of the graph of a polynomial function. And that's the final thing we'll look at in this section. But since I'm nearly out of time, we'll continue that on the next video.